I'm Mitch Conover. Today, I'm going to be presenting a paper that we just recently published in JAMIA's March 2025 issue. This paper was published in collaboration and built off of work done by Patrick Ryan, Martijn Schumi, Young Chen, Mark Suchard, George Ripsack, and extends all the way back to sort of some of the early Odyssey legend hypertension work. This paper is called Objective Study Validity Diagnostics, a framework for requiring pre-specified empirical verification to increase trust in the reliability of real-world evidence. Give me a moment to advance my slide. So we've spoken a lot in various Odyssey forums about sort of the reliability crisis affecting real-world evidence. So we have this question facing us for any given real-world evidence study. How do we assess the reliability? One approach is to use objective diagnostic metrics. So one that would be familiar to many people in the group would be the standardized difference of means, which allows us to compare covariate distributions among exposed and unexposed patients after analytic adjustment. One heuristic is Peter Austin's requirement that the standardized difference of means be less than 0.1 for all of the covariates assessed. So broadly, when we talk about objective diagnostics, we can build on sort of the principles of evidence dissemination in the legend framework, and we do so by proposing objective diagnostic measures should be used to evaluate and report validity of observational findings by either one of two approaches. One, interpreting objective diagnostic results before unblinding study results, or two, only unblinding results from analysis for which all objective diagnostics pass thresholds that are pre-specified before we complete the analysis. We further propose that all diagnostic failures should be reported alongside the unblinded results. So in the scope of our paper, we're going to be discussing sort of 6 diagnostic metrics that are implemented in comparative cohort studies by our Strategist software. In particular, I'm going to kind of zoom in today and focus on covariate balance, again, the maximized standardized difference of means we discussed. I'm also going to show some brief results from empirical equipoise, but we have other diagnostic metrics like expected absolute systematic error indicated by the negative control distribution, generalizability standardized difference of means, and also the minimum detectable relative risk. So again, we won't go into depth for all of these, but in the paper, we provide conceptual overviews of each of these. We evaluate sort of the threat to validity that's assessed by each metric and considerations or references when you're thinking about specifying diagnostic thresholds. So very briefly, again, the paper provides sort of an overview of the threat to validity. So in the case of covariate balance, the maximum standardized difference of means metric, we're worried about the confounding bias implied by an imbalance after an analytic adjustment between exposed and unexposed patients with respect to baseline covariates. We won't get into the metrics, but on the far right, you can sort of see the threshold guidance proposed by Peter Austin's heuristic that the maximum standardized mean difference should be within 0.1. At the bottom, we sort of show a figure of how this displays in our software, but you can see this would be an example of sort of failing where after analysis, we see a lot of these individual covariates indicated by the blue dots above that red dotted line showing problematic imbalance. So as a sort of thought experiment, what we did was we reused the legend hypertension results to sort of conduct a methods experiment where we applied various diagnostic metrics to a large set of negative control exposure comparator outcome triplets available in the legend hypertension results. So just a very brief overview of the legend hypertension study. If you recall, these are on-treatment comparisons of various antihypertensive treatments conducted across a large research database or a large database network. And they use large-scale propensity score adjustment to control for confounding. And most importantly, had a large set of negative control experiments where we theoretically know the results should be a null finding. And we use that negative control distribution to conduct empirical calibration and account for residual systematic error. And that negative control distribution can also be used to sort of measure systematic error. So imagine we have these 11,000 negative control analyses from Legend. We implement various diagnostic thresholds shown here. Again, we're going to focus today on empirical equipoise and covariate balance. But basically, we applied these different diagnostic metrics and we assessed their distribution across the different negative control experiments within Legend. So just to give you sort of a granular idea of what this looks like, the covariate balance plot, or the covariate balance metric is shown here. So just to kind of orient you, on the left two panels, we have basically the analysis before applying any restriction on a diagnostic measure. So we haven't restricted the analysis. We haven't required that covariant balance is less than 0.1. And on the right, we show the results if we exclude all the analyses that failed our diagnostic metric of requiring covariant balance less than 0.1. So at the top, you can kind of just see a histogram showing the distribution of standardized mean differences across all of those covariates across all of those negative control analyses in legend hypertension. And you can see a large share of them just don't meet our threshold and would be excluded if we apply this diagnostic restriction. And then on the bottom left, what you're seeing is, in the bottom panels, what you're seeing is a blue dot for each negative control experiment, plotting the hazard ratio against the standard error. And most importantly, what you see is the orange region is showing after empirical calibration, those negative control experiments that generate an incorrect non-null finding. And so what we can see is if we measure the systematic error and bias with the ease statistic of 0.38, when we restrict on those things passing the diagnostic criteria, a little less than half of things actually pass that diagnostic criteria. And we can see that we improve the ease slightly to 0.28. So high level, here are some of the results just for a few select diagnostic metrics. What we're showing here is basically that the covariate balance metric, when we apply no diagnostic restrictions, we have an ease of 0.38. Among the 42% of analyses that pass the covariate balance metric, we have an ease of 0.28, so a slight reduction. When we look at equipoise or empirical equipoise, sort of the Walker criterion of propensity score or preference score overlap, we see that an equipoise requirement that half the population be in equipoise is very restrictive and reduces the amount of analyses that we unblind dramatically, but does a very effective job of controlling for systematic error. When we explore a less restrictive equipoise criterion, we include many more analyses, but again, do a less effective job of reducing that systematic error. And we can see if we apply sort of a whole host of objective diagnostic metrics, we can eliminate sort of all of the systematic error estimated by the negative control distribution, but it is fairly restrictive and reduces the number of studies we can unblind by quite a bit, with only 13.9% passing. So the key takeaways, just want to mention that objective diagnostics are very important for evaluating and communicating the reliability of evidence generated by observational studies. This applies to large-scale evidence generation, but also to just one-off individual studies where it might be even more important to sort of establish a common reference. And then more work is needed to identify new diagnostics and establish their use across different study designs, for example, the self-control case series, and also provide guidance for diagnostic thresholds, especially in a setting where we're using multiple diagnostics at once. Thank you so much.